this will be, I think it's section 6 and 7 in the book, but finite sets in countable and uncountable sets. Let's start with a definition where a set is said to be finite if there is a bijective correspondence of A with some section, and we had defined what sections are of the positive integers previously. So some section of the positive integers. So that is A. It's finite if A is empty. Well, that's trivial. Or we have the bijection. There is a bijection that takes the set A to a section of positive integers. And so that would be for some n in sequence. So in this case, this has cardinality 0, and you would say this has cardinality n. So that's how they're defining finite in this case. So just and the idea of finding bijections, and so by the time we get to the uncountable versus countable stuff, it's going to be lots of whether or not there's a surjection from integers onto what you're doing versus injection in the other direction. But for finite, that's all we care about. We just have a finite set, which they're going to go by section. So then there's a lemma, and actually I think I'll prove this. This was a good lemma to prove. It's going to take up some space, so actually I'll erase this. I should have done it up on the top. Okay. So lemma, we're going to let n z plus, and we're going to let the A naught be in our set A. So A is a set. Then there's going to be a bijection. We can call it F. That's going to take A 1 to n plus 1. If and only if there is going to be a bijection G that's going to take A without the element A naught from A and mapping that to the section reduced by 1. So proving the obvious, per usual, with this kind of mathematics. So we're going to first suppose we're going to go the converse direction first. So we're going to show this gives this. So we're going to suppose that G with A without A naught to 1 to n. And this is going to be bijection itself. So we're going to then define f a to 1 n plus 1. We can specifically define this where f of x is just going to be g of x for all of the x values that are in A except for that one element. And then what we do for that one element is we simply reassign that to being the new one. So if we have fewer elements, we take everything in here per usual because G is already defined. And then now whatever we took away, if we're going to add that back in, that's just going to take the place of the last. So this is, that's going to be bijection. So we show this is bijection. And now we can go the other direction. The other direction is a little bit more complicated. So now we're going to assume the other way. We're going to assume we have f a to 1 n plus 1. So the question is going to be finding a way to talk about removing an element and then reassigning all the elements through some specifically defined bijection. Or we have to show that it's a bijection. We'll define a function that's going to take reassign the taken away element to this new section. And then just make sure the labeling is general so that you don't have any double counts, right? So if we assume this, so if f of a naught is n plus 1 already,
We're done. It's easy.
yes, exactly. Then and then this was interesting. They decided to use that restriction language. So f restricted to a minus a naught is the desired bijection. So basically, yeah, once this is, that's how we want it to be. But it was cool because up until now, I hadn't found a way to apply why we needed restrictions or why they defined restrictions. So that's actually kind of a slick way to do it, without having to specify all of the English words. That's just all contained in that. So then obviously the not fun case is when, so we can say that otherwise, we're not going to assume fa naught is the n plus 1. We're going to let fa naught equal some element m now. And then to show, instead of saying that m is not equal to n plus 1, we'll do that by then taking a different element, a1, and then making this be the element that goes to n plus 1. So we're not going to double count what goes to n plus 1. So then it's kind of like I just explained, it's given that these are not the same, so we won't double count. So now we can define, so now we're going to define h that's going to take a to the one with n plus 1 in it. We'll first take that a naught. And then where we want a naught, instead of going from to n, we'll reassign it to n plus 1. And then the reason we can do that is because since we have already shown that these are completely distinct, that we can simply just say, okay, well, I'll make this go here and you go there. So we don't double count anything. And the only things we're switching out is what wasn't going to n plus 1. So this is now going to n. And then because of that, everything else is fine, because that was the only issue. It's either an issue or it's not. And everything else, h of x is equal to f of x for all x in basically the rest of the elements. So a, that's not involving the a naught and the a1 that we've already dealt with. And in this case, this is a bijection. So we say since h is a bijection, and we have the straightforward case, because the reason why we did this, it was so that we could basically, we just want to get back to the trivial case where we can say that our function or our map is taking a naught to n plus 1. So now we're back to that with this right here. And we have the straightforward case, h a naught equals n plus 1. Then the restriction again, restriction, h restricted to a without a naught is the desired bijection. bijection of A without A naught with the section through N. So that's a fun one.
I like the way that you interchange them rather than just shifting.
Yeah, I thought about that, but that's a little boring because it overcomplicates everything. Well, because the only because I think it came from the way I understood the lemma originally. It's just simply, okay, well, that seems pretty straightforward, right? If you have a finite set of cardinality n plus one, and if the only difference, that means if you take away one of your elements, okay, you just decreased your cardinality by one. So in that case, just pick something to take out, and then that was
Nice.
it's nice. Yeah. Okay. The rest of these are not so nice. So I'll just list the theorems, because the nice ones are in the countable and uncountable section. I think in terms of pace, I'm gonna start settling into like a 3-section a week kind of rhythm, because that will get me through all, like through the core, and then I'll be able to do ticket up theorem, I think. Because then over winter break, I can clean up whatever, applications I'm interested in before going to the algebraic part in the spring. So more or less, I'll see probably 80% of the book, which is respectable, I think.
Yeah.
Okay, so just a few theorems. Or most of it's kind of, I think, theorem and corollary kind of business. So we have let A be a set, and I suppose that there exists a bijection if A goes to, and then a section through N for some N Z plus, and then we're gonna have a subset of A. Then there does not exist any bijection that takes B to the same section of those positive integers. But provided that we don't have an empty subset, so provided that B is non-empty, there does exist a bijection that takes H, where B is now going to a section through M, so long as M is less, so for some M is less than N. So that's, I don't, I mean, they call it a theorem, but basically this is proper. I use this notation for proper instead of, I don't like the way he does it. But yeah, this was pretty intuitive, just from the previous proof. If you have fewer elements, well then of course you can't go to the same thing.
Right.
So honestly, this probably should have been proven as a corollary to the other one. And then, but you can still have, if it's gonna be a finite set. So long as, I think another specification that they could have made though, is that, and they do this in the proof, but essentially they let n be equal to 1. The only issue with that is then your proper subset is empty. So then,
Why would they, do they do it by induction or something? Why do they let it?
yeah, the text wanted to do it inductively. So then they say, okay, well, if I take A has a cardinality of 1, so A is going into 1, and then your subset, your only possible, like proper subset is gonna be empty. And then if it's empty, you obviously can't go into here, and then, so they try to do that, and then they show that they assume that it works and push it, but I don't know, it felt a little forced when it probably could be proven just using, like, citing the result from the previous lemma. But yeah, they turned it into a whole a whole maze of work there. Okay. So then a corollary is that if we have A finite, then that gives that there does not exist a bijection of A with a proper subset of itself. A proper subset of itself. Basically, if I understand this correctly, the editorial side of this is a little clumsy, but they basically just take this first result that they call the theorem and then relabel it as a corollary. Because that's essentially what he's saying. B is a proper subset. You can't have the subset. I don't know, but because then when he proves it, he basically just cites the work that's done in the theorem. So then the corollary is that the positive integers, that set is not finite. So, and then we get into the different kinds of, it'll be countably infinite instead of uncountably infinite. Actually, this proof is kind of cute. I'll just list it.
They do a contradiction based upon that.
Yeah, it's just a contradiction. So they'll say, okay, well, if we can try to do it, right? So if we take the plus 2 z plus, and we can just take out a random element, whatever that is. We can define this by we can assign n to n plus 1. You just shift everything. But this is a bijection, so this is a bijection. The only issue is that I'll specify that z plus without this element is a proper subset of z plus, so it's a contradiction to the previous. So yeah, that was kind of fun. And then another corollary is that the cardinality of a finite set A is uniquely determined by A. It's uniquely determined by A. And then if we have B some subset of A, then intuitively that cardinality is going to be less than the cardinality of the subset is going to be less than the cardinality of the set of privileges. So lots of these corollaries are basically just establishing the assumptions that we would otherwise have made in an algebra class about cardinality. But it was good to see it all from the theorem at least. This is a good eraser. The one in my bag does not do this well.
Yeah. So you get to a point you can understand why authors would say clearly and obviously, because they know it so well that they don't understand there's really nothing to prove here because it's.
Well, there is something to prove for the undergrad.
Yeah, but for someone who's not in the know, it's like magical.
Yeah. Well, I mean, it is fun to see it.
Yeah.
For the first time. So this was a good set of conditions. So condition for finiteness corollary is this: so long as we have B not empty, then we have the following are all going to be logically equivalent. So the first thing is if we say B is finite, then that's logically equivalent to there being. So there exists surjection from the section to B. So that's going to go on to, and then that's also logically equivalent to there being an injection the other direction. So an injection from B. So I liked that the way that worked, kind of a thing. This honestly was a little bit cumbersome for finite, but when it came between countable infinity versus uncountable, that's where it started to make more like why you would use this kind of properties, because when you like establish two different, so it's like if this is your B and this is your section, then if you're able to go on like in this direction, if you're able to cover onto,
Yeah.
well, that's good because you're supposed to be able to go to your section. But more importantly, if there needs to be a one-to-one correspondence in this direction. So you don't necessarily, the only reason why the injection stuff is kind of tedious is because it's kind of implied that with a finite section, you just assign everything. But the moment this becomes countably infinite, then it would make sense, okay, you don't have to go into every single one of the elements in the countably infinite set, but you will have to be onto going the other direction. So, but
so the section could be bigger cardinality than B in this case.
Right, because B being finite is only guaranteeing the existence of a particular bijection for some n. So this n, this section could have a bigger n essentially than whatever this n has. But so that's why it has to be injection. You can't necessarily assume it's gonna go both ways. But
okay, so they're giving a little more freedom.
A little bit more, yeah.
Yeah.
And it's more broad language,
The
yeah.
weakest condition that you can get away with is naked.
Right. He seems to be very interested in doing that for lots of set theory things here. And I think some of that was changed from the first edition at least. So
Okay.
But then the last little thing is that finite.
He probably got letters.
Yeah, probably. Finite unions and finite Cartesian products are intuitively and can be proven to be just finite. So, well, so long as the sets are so of finite sets are finite. And there is a way, he did like an interesting, he defined a very specific bijection to kind of illustrate a point for some other section that's way in the future. So we'll get there when we get there. Okay, that's all the finite stuff. Now the fun stuff. Put a little bit more meat on the bones instead of just telling people that there's different sizes of infinity. Yeah, make it mean a little bit more. Which also, in one sense, though, because I saw there was a paper where they show there's an infinite number of infinity sizes. That's good. That I would have to take a few years to really appreciate that work, especially considering how embarrassing long it took to understand this. Okay, so we're gonna then define in typical math style, a set A is said to be infinite if it is not finite. It's not finite. Very nice definition. And then it is said to be countably infinite. Countably infinite if there is a bijection. So they're gonna reuse the idea intuitively in some sense. So now instead of going to a section, we just go to positive integers. So they probably saw that coming. Let's see. So they do, and they show basically that the set of all the integers is countably infinite. And actually, this is really cool because so Frawley, when he was doing algebra, he started with the integers, and then he actually said positive integers. He showed that those have the same cardinality, so that it's cool seeing it the other way because fundamentally that does make more sense because this is a construction that comes from defining the positive integers as in the intersection of all the inductive sets on rails. But so integers countably infinite because we can find a bijection that's going to take all of the integers to the positive integers, specifically defined by f of n where this assignment was actually done as an example in the algebra book, where we take all the evens and associating the evens with the positives, and then the odds with the non-positives. So that's the bijection, and this is the relabeling. So like when they stagger the relabeling.
So do we need the equality on the top one?
Well, so that's just a matter of like convenience and choice. So instead of having, so since it's -2 and +1, this is just guaranteeing that we cover what 1 is, because if we need 0 here so that we can get 1 minus 0. Because otherwise, if we put the equals here, then we're including 0, but we can't get 1 unless we shift this.
I see.
Yeah.
Okay.
That's more of just like a little annoying technicality for getting 1. Okay. So then we define a set is said to be countable if it is either finite or countably infinite. That's pretty straightforward. And then a set, they say this so that we can say that a set that is not countable. That's going to go on. It's a set that's not countable is said to be uncountable. It's nice. You read enough math at a certain point that the way that they decide to define everything is at least predictable. Okay, there are these conditions that are going to be nice for testing for the countable infinite or countably infinite. It's gonna be reminiscent again of the conditions that those like the logically equivalent statements for the finite ones. Here, so long as again B is not empty, B is not empty, then the following are all going to be equivalent. So if we have that B is countable, then there's now going to exist a surjection that will take the positive integers onto B. So the only case when this would not be onto is obviously when this is no longer countable. And then but the other direction, so then going from whatever your countable set is to the positive integers, this has to be an injection to preserve loss of generality, so you don't lose generality. So injection that takes your countable set to the countably infinite. So in one sense, this is just describing this is countable, but this is the biggest countable you're gonna get. So that's always going to be onto all the other countable ones, but you're not necessarily always going to be.
It could be finite.
Right.
It's interesting. I like the parallelism between this one and the previous one.
Yeah. No, it was good because I didn't really understand the finite
Right.
one until I got to here, because this for some reason made more sense than trying to take the sections, because I forgot to make the consideration basically that the finite set having a specific n didn't need to be the same n for the section. And that I kind of put that together approximately 5 minutes ago, so it's good. It's good to go over it multiple times. Okay, an lemma from this is that if C is an infinite subset, so C is an infinite subset of the positive integers, then C is countably infinite. So there's lots of different ways to think about that. You can think about it in terms of basically this idea, where B is countable, but you're going into, because you're a proper subset of, or just intuitively, because if you're smaller than something that's countably infinite, there's no way it's going to be not countable or like uncountably infinite. And then, see, then the corollary is a subset of a countable set. Well, set is countable. And that's pretty straightforward. So we can suppose that A is a subset of B, where B is countable. So if this is the case, we can just take this because we can cite this theorem and say, okay, well, if countable, then there's going to exist this injection. We could say then there is an injection. To be countable, we're going to take the set, and that's going to be into one-to-one with the integers. And the restriction, because A is a subset of B, so we'll restrict this injection to A. This is an injection that takes A. And then you just go back and say, okay, well, we have an injection, so this is going to be countable. So A is countable. Cool. Pretty straightforward. And then the fun one. So let's see, what time is it? 40. Okay. I won't be able to do all of them, but I think I'll try to do these two because these two were the most fun for at least to do. They're all really fun. I enjoyed doing them all, but those were the ones that specifically, at least I think I had the most fun because I struggled with them the longest. So then it was more satisfying to figure out. But yes, it is kind of a breakneck pace to be seen. Topology. Okay. So the first is I think I like this just because it helped me review my skills from the higher algebra class. So it was seeing that those skills are still relevant and that the positive integers with themselves and the Cartesian product, you can show that this is countably infinite. So it will suffice to show from that previous condition theorem. We just need to find, want to show that there is an injection that's going to take the Cartesian product, that's ours, that we're interested in, to positive integers. And so what we can do, we define the map to be f and m, so because we need to be able to take two inputs, and we'll spit out 2 to the n, 3 to the m. Okay, so now to show injection, that's where there's the review. So we're going to suppose that two of these outputs are the same. So 2 to the n, 3 to the m, and we'll use p and q. So 2 to the p, 3 to the q. So then it's kind of like we motivated by contradiction. So we're going to say they're different. So if n is less than p, so if they're not the same, then we have the issue then of doing 3 to the m. If we can move this over and p minus n will be positive, so 2 to the p minus n 3q. But this is a contradiction. Contradicting the fact that 3 to the m is always odd. And this is always going to be even because p minus n is positive. Leave it at that. Okay. And then we just contradict then that. So we use this fact to say that, first of all, that force is 2 to the n. to be the same thing as 2 to the p. So that's why we can then assume that if m is less than q, then we're really saying, because these are the same, so we have 3 to the m equals 3 to the q, we divide the m because the m is less than q, so we have 1 equal to 3 to the q minus m. But that's also contribution. Because that says that q equals m, but we assume that m is less than q. Okay. So then this is an injective map, so then we can take the Cartesian product over to the positive integers. So it's countable.
That's nice.
And then it's infinite, it's not finite, so it's countably infinite.
Because traditionally you show how you can actually do a bijection. But just to doing the injection is kind of cool that you can just do that. I like it.
Well, the only reason you can do that is because you had the hardware from the previous. So it does some of the nicer results have a little bit longer buildups, but yeah, no, this was fun. It was a good exercise.
That's basically the rational.
Yep. I think there was something where you could essentially do the same thing to the rationals as well. You change the definition just a little bit to accommodate, but the map is logically pretty much the same. Okay, this one is this is the only time that I did something with induction and I didn't feel sick after doing it. Because it's so elegant that when you get to the actual thing, so a finite product. It's also a really useful theorem in general. So a finite product of countable sets is countable. So inductively, we're going to first show that it's true for just the smallest case. So we first show that A cross B is countable. Well, okay, I'll do it in a way reminiscent to closure. So let's say if A, B countable, then A cross B countable. So this is trivial, so the result is trivial if either A or B is empty, and then otherwise we can choose surjections now. So instead of using the injection property, we'll use the surjections that go from the positive integers to the sets. So here we have F for going to A, and then we use G for positive integers going to B. And then we'll have that H, which takes Z plus cross Z plus to the Cartesian product. So long as we define it by, so defined by H, so we have a coordinate from A and then B. Since these are already surjective, though, we can just use what they're already going to map, because that's going to be onto. So this is surjective. And then A plus B is countable. That's the first case. So then we proceed by induction. So we'll assuming that take a product, and we start with one less. So A1 through AN minus 1. We'll assume that this is countable, so long as we have AI countable, and I'll just say to be clear, if each AI is countable. to meet the hypothesis of the theorem. So we prove the same thing. For product that goes through n. So a1, increasing this by 1 now to an. Instead of doing n to n plus 1, it was more aesthetically pleasing to have it stop at n. That was more just an OCD thing. So we first note that this is the slick trick. It's so cool. So that there is a bijection, because this is the only instance in which proving the first result actually was useful for future consequences. So we cite this subresult that's inductive to get to that it runs the entire rest of the induction here. So we can take G, which is mapping all of them, right? So all of the sets together through n, to itself. But we'll express this as being a1 through n minus 1 first. So we'll take a pit stop. And then that's just, with a sub n. But the nice thing is that you can treat this as one set. So now this is a set and a set, but we already showed that two sets can be countable. So this will be defined by G, where you take that tuple, so x1 through, xn is going to then be x1, xn minus 1, and then the xn is then treated like that. And then because a1 and minus 1, what's nice is we're using the countability of that from the hypothesis. This is countable from the induction hypothesis, and an also has to be countable, because again, in the hypothesis, every single AI needs to be countable. Then the product of these two sets is countable, as proven initially. And so that gives that the whole thing through n is countable. So that's probably my favorite one so far. Because that's crazy. Because I did not see that one coming. I wasn't able to solve this on myself. I had to see this.
Okay, good.
But when I saw this, it took me a second to accept that this was still going to be surjective. But then I was like, oh no, it's the same. It doesn't matter that you put you can just associate every xi to xi regardless, and it'll still be the same. But yeah, I think it was confusing at first because the textbook doesn't provide any explanation. The textbook basically thinks you just know everything. So they show this, and then they basically set this product up, and then it's like they drop the square, which technically that was enough. But yeah, it took me a while.
Yeah, it's nice.
But yeah, that's really fun. Favorite one so far. And so I'll probably try to do I think I'm going to skip the recursive. So there's an asterisk next to recursive definition. I skimmed it, and it's nice, but that looks like more of they're trying to do it like a computer science kind of an application thing. So I'm just trying to cut to the
real stuff.
Yeah, the topology stuff.
Well, cool.